to be three-dimensional, according to our thing.
Well, yeah, I mean, if you look at quantum mechanics,
so you have to say entity. Entities could be quasi-particles or anything like that.
What do you mean by entity?
Entity means this is existing, but it may not be real.
Oh, okay.
It
Cool.
may not be real. It could be imaginary. It could be, it can come back into real. But particles means it's real, you know. From my point, that's why it should be. Particles are observable. Observable. The real is observable. Imaginary is not observable until you rotate, do something to bring it to the real.
Yeah.
That's why you have to redefine it. I think there's a confusion now. Observable is something that you should be able to observe with either experiment or something, like gravitational waves. Because we can see in the real dimension, we are able to see that. If it is the fourth dimension, we cannot see it.
Yeah, I do really like this idea of like using the fourth dimension to explain a lot of those kind of, what would you call them? Not really inconsistencies, but
so it's like a Minkowski space-time type of thing.
But that's what I find, like with space-time, I haven't really drilled down into that enough to you know, what little I know about it, I'm actually kind of shocked that it's at all been adopted, because it seems like the kind of the craziest idea that I could think of even. And like if I was to say it to somebody, they'd just be like, yeah, that's ridiculous. But for some reason it's well accepted. Do you know what I mean?
Oh.
Like for instance, if you were to take how to say this? If you were to take you know those surveyists who try and triangulate something on the ground, so they take angles and sine and cos and all of that. Like Einstein and Minkowski kind of suggested, hey, why don't we do that with time, so you can apply the same transformation. I think it's basically Pythagorean, that kind of thing, Pythagoras equation or formula, whatever.
Riemann, Riemann, yeah.
No, the Pythagorean. Yeah. So that one. Or the hypotenuse and all of that. So I think you apply that, but using a time, by adding in a time axis, that you could then triangulate the angle between two events in a kind of block time or space-time universe. And I think there's an awful lot of problems with that. And I find that it is a lot better to just simplify our systems by saying, you know, like for instance, actually, if I go back to here.
That's why we are going to do the spherical coordinates.
Well, hang on a sec, Rajan. Yeah, that might be a good point. But like, let's say you're visualizing. If I go back to what we were just in.
Okay.
Just to do it rotations. This one. So like, if I make a video of this structure rotating, where was it? Any of these graphs?
You already have a program to do this, right?
Yeah, I can do that. So if I made a video of this structure rotating, that's got time and the 4 dimensions in there implicitly.
So you can show how it goes out of visibility and come back into visibility, things like that.
Yeah, exactly. And so when you do that, and there's no trouble there really, but the point is that time is like as we perceive it in the ordinary sense. You know, you're not turning it into another kind of spatial dimension, even though that's not even accurate within relativity, which means that it's even more complex. It's even more abstract. So it gets to the point where, you know, I don't even think that's possible to computerize, like to simulate on a computer. And that kind of worries me, because I think like computers are pretty sophisticated at this point.
Yeah.
And they are also like, they deal a lot with maths. So if a computer can't simulate your theory, I think there might be something desperately wrong with the theory. Like, you know what I mean?
Yeah.
That's what I'm kind of edging towards at the moment. And there's some serious, like, you look at the issues with contravariant and covariant. I don't think they're called tensors, yeah?
Yeah.
And in those tensors, you've got these derivative terms, and each of those derivatives is a function, so it's infinite. And then there's an infinite number of functions, and then you have to plot all those in the tensors, and that's one point in the field.
Mhm.
So, you know, how you're supposed to plot anything is beyond me. Yeah, so
That's why we are going to do this way. I think we'll be able to pull up some things because I am able to pull up
but it sounds like, Rajan, that you're planning on using a lot of these
in my
covariant fields, are you not?
time. A computer will do like that, but it's not exactly. I mean, it's not exactly the same because when you translate algorithms and things like that, there are quarks in that. So, but we have to figure out compatibility problems, parity or compatibility problems may be there. We have to resolve that.
Oh
So there
yeah,
are some few problems that pop up. We have to resolve it. But I think the three-dimensional the spherical coordinates is going to be the key when I worked out. Cartesian is very hard, not possible. Because rotations, we can deal because, like I said, it's a clockwork. The particle is seen as a clock, and
yeah.
when you see as a clock, you can figure out everything. So I'm able to figure out it's a micro clock or macro clock.
Is it
Uh,
a clock in terms of like an Einstein clock that it's running slower or faster, or is
yeah,
it clockwork as in something else?
yeah, it's more like from quantum. For example, this circuit, what I say in that one paper also I say briefly, when you go to quantum level, it becomes this circuit, this PDP circuit assembly we are showing, right? When you go to relativistic level, right, then it becomes like a particle. It behaves like a particle. So it breaks down. That's what the magic square and all come later on. I don't specify that here. So when you go from relativistic level to quantum level, it breaks up into monopoles and these particles, right? Like point particles. Whereas when we go into relativistic level, it
Yeah.
becomes like photons and phonons.
Okay. Yeah.
So the energy, what I'm saying is the energy is conserved that way, energy is stabilized that way. The lower level energy gets stabilized because you have to have a circuitry, something that maintains that energy, right? So that this particular circuitry maintains that energy, it can generate the energy required.
Mm.
And when you go to higher level, so it becomes phonons and maintains that energy. So you can explain why it should become photons and phonons from this point of view. Why it should become higher levels. Our graphics itself shows, these things combine and they form neutrino and eventually photons. So when you go to higher levels, it combines automatically. It has to become photons or phonons stabilize that particular energy. So that particular energy level then becomes that particular mass or that particle with a mass. So it locks in that particular thing.
Okay.
Uh, as a photon, it locks in that energy. The photon will lock in that energy.
So in
Phonon will lock in that energy.
you're
But
saying
when
that,
you go to the quantum level, it kind of splits apart and becomes this monopole and the particle circuit. So you can what I'm trying to eventually, when we simulate, you can show that is like magic square symmetry. What happens is, like I said, prime factorization, right? So at the lower level, these monopoles and they start as factorization, prime factorization. And when factorization is complete, it becomes like a magic square symmetry. Okay. So
Okay.
from this circuit, it forms like a magic square symmetry. But the magic square symmetry itself is not a perfect symmetry. So it has a breakup. It's not a regular crystallographic symmetry, you know.
Sure.
So it breaks up, and then after it breaks up, then it forms photon and phonons, which helps the formation of crystal symmetry. So these are the levels. So it goes from these 3 or 4 levels are there.
Okay, but how do you yeah.
So it's all depending on the energy levels that it locks in.
Wait a second, though, Rajan. So you seem to have a disjunct or a disconnect between the quantum and the relativistic thing.
There's a discontinuity at the bottom level, but the discontinuities are because of functor, right?
Okay.
So each one is like a
rather than go but isn't the whole point of physics to like unify those two things?
Yeah. So how does it become together? Yeah, how does it come together, right? So what is the flow between, what's the connection between that and the relativistic, right?
Yeah.
Important to realize that these two have problem. Quantum level explains something, like I was saying last time, and the relativistic level something else. So that's why you have vacuum catastrophe to some degree, right?
Okay.
But so we have to come to that, but our thing tells a way to get out of it. So we realize that that problem is there, right? First we have to say, okay, that's the way people derived it. And our thing also comes to that, right?
Yeah.
So there is a disconnect between the quantum level and the relativistic level. There's a disconnect. So it's consistent with what we are seeing now, right? But how do we resolve that inconsistent, that disconnect? We have a way to, that's where functional comes into picture. The functional is the time. What happens is the clock, okay? The clock at the lower level is different from the clock at the bottom. The clock at the quantum level is different from clock at the relativistic level, right?
Why is that though?
Because the clock is based on this circuit at the quantum level, the PDT circuit.
But the clock can't be based on the circuit.
Yeah, that means that the circuit is going and is creating a clock. So all the spherical rotations.
But hang on, is the clock time?
Yeah, eventually we can translate to time.
But how is the circuit moving if it's the thing that makes the time?
Yeah, actually that's why I say, so at the quantum level, it's the event that makes the time. I explain it differently. It's not the time that makes the event, the quantum level. No.
It's not even really makes sense. I mean, surely an event.
If the event, okay, what we are saying, we can almost prove this one. If the event doesn't happen, the time doesn't happen.
Sure, but is that not just
quantum level? Quantum level.
Right. Yeah. No. I think this is also that we spoke about this guy before. I've forgotten his name now. But yeah, that's part of loop quantum gravity. It's a key factor in loop quantum gravity that the events create the time and space.
Yes.
So it is I think it's even kind of accepted among physicists and stuff, because they're looking for a way to get rid of time and space out of their equations, because nothing that they're doing makes sense.
Yeah, actually, I kind of eliminated the possibility in my mind, simulating in my mind.
Yeah.
I kind of could freeze and show that in my mind. Okay, now we have to show the computer is slightly different. It's a communication. This is an operation in the mind, right? I could freeze and then show that if the event doesn't happen, the time doesn't happen. I could actually prove it in my mind.
But I would like to...
At the quantum level.
I'm thinking, yeah, okay, maybe there's something to that at the quantum level. I'm just playing devil's advocate here, and I'm like wondering, is that not kind of, what's the word, like semantics? Like we're saying, okay, event is different to, an event is something that happens in space and time.
Yeah.
And so you can say, well, the event can't happen if there's no space or time. So you could look at it from the other perspective as well, couldn't you?
Yeah, event is not the same as time. See, event is event and time are different quantities. Okay, event is something and happening. You know, time is the flow that connects between events. So there's one event that's happening, right?
Well, that's to suggest that events are somehow quantized or something. Since they are quantum level. Yeah.
And this circuit will say that, yeah, it could be quantized. We have to prove it after simulation. That is it really quantized? That's one aspect that if it falls out of the simulation, great. Otherwise, you have to find a way to prove that.
Okay. Right. Does the event have duration or what?
Yeah, that's a good question. So the events, okay, what happens during the event? That's one interesting thing. Does that?
Okay, you've dropped out. Go on. We lost you there for a bit, Rajan.
Tunneling events, for example, right? Are you able to hear?
Yeah, just for like maybe 15 seconds or less, we lost you.
Oh, okay. Okay. What happens is the quantum level, right? There's like something called tunneling. Tunneling is like degenerate states, that movement of like electrons, the degenerate states. The same energy levels tunnels between the two, right? It goes from one level, it jumps automatically. It can be in this both state. That's called the Bell inequality, or all the entanglement all comes there actually, some ways. So what happens is that the particle, for example, can be on this level or on that level, almost simultaneously. That's what it says.
Yeah.
So at that time, the time is the same. The time is, there is no duration there at that level. So there is not, only the event is happening. The time is kind of frozen. Okay? But once the event happens, the time starts flowing.
Huh? Is that because you're taking a moment of time which is so small that there is no time?
Yeah, actually it does question about continuity of time. So time could be discontinuous at the quantum level. Yes.
Sure, right. So you get back to the idea of the chronon, which is the particle of time. Yeah.
Yeah. So there is like chronons, it has to move like quantum level, quantum. So which means that at that level, the time doesn't move continuously. It's not that continuum. It's discontinuum. There's a discontinuity.
Right. And how does the prime number thing?
Yeah, comes into picture. So it has to do this prime factorization.
Why?
And that's the event. So it has to produce that in order for the time to pass. If the prime factorization doesn't come, the time cannot move.
Give us an example of so like you take
take an example of our cells, right? We live, you know that we live because the cell is dividing. The cells stop dividing, we don't live anymore.
Okay.
We don't. Yeah, the biology cannot exist anymore.
Fair enough.
That's why we die, kind of, you know.
Yeah, I hear you.
So the cells have to keep dividing all the time. In our lifetime, it has to keep dividing in order for us to be surviving, in order to be alive.
Yeah.
Okay. Like brain cells, all these things. Otherwise, it will be brain dead. The brain cells doesn't divide, will be brain dead, like that. And then, and the body, the body can still divide. So that is kind of very similar situation.
Yeah. No, you've made a good point there, but like, how do you relate that back to the quantum thing?
Quantum level.
Why is that? Sorry, related to the prime factorization.
Yeah.
Why? So let's say I give you a number like. How do you work? Like, let's say I give you a.
Like a 35. Like a 35. Let's say
35
number 30.
is not a prime number.
Yeah. So you divide into 7 times 5. So 7 and 5 are prime numbers.
Yeah.
So you divide to 7 and 5, right? In some form.
Get you, yeah.
Then you get factorization. And then 7 and 5 form some kind of a magic square symmetry.
Hang on, how does that happen?
We have to figure out what is. That's what you and I have to figure out. You are good in magic square. How does 7 and 5 become magic square? What kind of a configuration gives a magic square for 7 and 5? We have to still figure out. I think there is. Intuitively, I can think of some things, but we have to practically we have to think of a real magic square assembly where symmetry where it shows 5 and 7.
Right. Well, you could just spitballing here, but like obviously a square has to be. I mean, if you multiply 5 by 7, then you get 35. That could be a square.
But the 7, for example, 7 could be, for example, crystal symmetry. There is a 7 symmetry. The 7 is, there are 7 crystal systems. You know that, right? Like body-centered, face-centered, and all these things.
Yeah.
And the 5 is actually what you call as in group theory. It's a non-existent symmetry. You cannot, in a group rotation, you cannot have 5-fold symmetry. You cannot get 5-fold symmetry.
Are you sure?
Yeah. Actually, there is a proof. I went through that. I did a little bit on that myself, and I want to publish that in material science. And there is a proof. We do some called group theory rotations. And in that one, you can show the 5-fold symmetry does not exist.
What about Roger Penrose's work into quasi-crystals?
Yeah, he may be using that. I don't know. But it's a well-known proof.
He has no. He has 5-fold crystals. They've made them in the lab, like 5-fold crystals. Yeah.
5-fold crystals may be there, but 5-fold symmetry is not there. It may be different.
But a crystal symmetry, 5-fold crystal symmetry.
Yeah, that does it. So what I'm saying that we then come to the point. Microsymmetry is possible. Microsymmetry. See, there is a macrosymmetry, microsymmetry, right?
Yeah.
So 7-fold, you can the 7 systems are micro.
Are you talking about tessellation?
What's that?
Like when you have this 5-fold symmetry with tessellations.
Yes.
Yes. Yeah. Okay.
Yeah, then it's possible. Microsymmetry is possible. That's what exactly we are coming to.
Okay. Yeah. Very good.
The 7 and 5, the 5 becomes that quasi-crystal thing. That Penrose is, you said Penrose. That partly proves the thing. That 5 becomes that, and the 7 becomes the macro level system, the macro symmetry. So it actually, the 35, then prime factorization, it becomes a macro symmetry 7, right? And micro symmetry 5.
Sure.
That's how it resolves that. So you have automatically micro and macro coming into picture. That's very important. So you have a quantum level and a relativistic level automatically.
Yeah, it says, okay, you could work it now.
You see that? Now it's splitting up. The 35 is splitting up into a quantum level and a relativistic level automatically.
Oh, yeah. Okay. And then there's also other stuff that I'm working on to do with like you could take...
recorder. Oh, okay. We may use this record actually later on. These are very important points we are talking about.
Sure. So we have I was just thinking there, so you have 7 and 5, yeah. And then you could create out of that the kind of parametric waveform using like those two numbers.
Yeah.
And that kind of relates back to torus, those kind of torus shapes.
Yeah.
That are...
So you can come up with a shape like I was thinking tesseract or something. Tessellation or tesseract.
Well, tesseract is a 40 square, yeah.
40 square, right?
Well, then you have those Lisa-Jew patterns. I'm not sure if I'm saying it right, but you know the waves. And those would relate to the... I'll have to look into that, Rajan, but there's possibly a direct route. That's a very small possibility using this method of parametric equations. Like I've been planning to use that in the work with the crystalline things anyway, so
yeah,
it could work. It could cover both. It would want to, you know.
We can incorporate into a program these things, you know. So automatically, when you later on, we want to build as basic programs, very simpler. Then we want to add on to it. So we should have enough flexibility to add on to the thing. We don't want to complicate everything, you know, put everything and complicate the whole thing. We just want to rotate it and see what happens, and then go to the Clifford rotation, and then move on to this type of factorization things, and say whether there's a then we can say, we can prove whether there's a discontinuum or disconnect between the quantum level and the relativistic level. If we are able to prove it, then we have indirectly. So the converse of that is the kind unification, right? The conjugate of that, the converse logic, and we have proved that it's discontinuum, but we have found a way to resolve that discontinuum, the disconnect, by understanding the prime factorization and magic square and the crystal symmetry. So there are like 4 factors. You have prime factorization, the magic square symmetry, and the crystal symmetry. And then the quantum, that automatically connects with the quantum and the relativistic disconnects. I mean, everything talks about wave function, right? The theory of everything, the final equation is a wave function, which puts together all these things together, you know?
Mm-hmm.
But we have to re-examine what caused the vacuum catastrophe, the quantum field theory versus I would think that general relativity versus the quantum field theory is what caused the vacuum catastrophe. They give totally like 10 to the power 128 factor of 128 for the 0-point energy or something.
Oh, yeah. There's a big issue with the quantum. How do you say it again? The
quantum field theory. Huh?
Sorry, the catastrophe.
Vacuum catastrophe.
Yeah, that's a huge issue, isn't there? There's like one theory is saying that the amount of energy is tiny. I think that's relative.
Yeah.
The one is saying that it's huge, which is quantum. Right. But and the order of magnitude, as you said, is huge. Like, yeah, it's interesting. I mean, I'm also a bit. I mean, I'm looking into this thing. I've been also very interested in prime factorization, not so much from the perspective you're coming at it from, although that is interesting. So there is some element where that might be good, and then it's kind of you know, you have these two numbers and one is bigger than the other, so it's how to kind of square the I'm thinking in Irish here, Drunalo rectangle. You need to square that rectangle. So
there's also Mobius. You know the Mobius curves, right?
Oh yeah, Mobius strip.
Mobius strip that you have for when you rotate, you get the toroid, all the other shapes. You can.
That's a nice word, though, isn't it, Rajan? Drunalogue.
Yeah, drunalogue. It's an Irish word.
Yeah, it means a rectangle. It's an odd word. It's nice though. So, drunalogue. There's a couple of nice Irish terms in mathematics that my brain just will not. I only think in Irish in those terms. So, okay, yeah, like if you could. So, for instance, you can unravel the torus, but you're going to wind up with a rectangle, you know? You're going to have some nice diagonalized patterns, which...
It's like 4-dimensional rotation or something, right, of a rectangle?
Kind of, yeah, I suppose, if you think about it like that. I mean, you could technically just multiply, like square the two values to create two squares, obviously, and then try and work with them to create like a higher dimensional torus. I don't know if that's possible.
I would think our rotation, once you program the rotation, and you put in the shape of a rectangle, and this rotation, the computer runs the program, it may be able to create a torus.
Yeah, but what if the rectangle was already a larger dimension? So it's a rectangle.
Anyway, we have to put our square. I mean, actually, our circuit will be like a square or a circle. That's why the finite element. I also put it in there. The finite element. What happens? What are the elements? I'm describing briefly in the revised manuscript, because to satisfy the other reviewer, I said that what we are going to do with the finite element. We identified what the cells should be. The figure 10, the last graphic, right, is the best one. In our
figure 10 is this the one that I made for you?
Yeah.
Which one is that? The one with the circle or the?
Yeah, the one with the dipole in the middle, and the thing. What happens is that becomes the dipole becomes the node, and the other one becomes the cells.
Yeah, I kind of see what you're doing. It's kind of like an alternating circuit or something. Yeah. But there
so I said that we can choose that for finite element modeling, you know. So that will, that will help, because we went through this exercise of scenarios to figure out that. And then if we can do that modeling, and I rationalize, I justify why we should use that, and then we go ahead. Now we can use that and maybe model. Now you can think about a rotation itself. It's a program you can start with, and then you can do the finite element modeling later on, and fit in together with Clifford algebra and all that. Slowly we'll introduce the complexity, but we'll start with a simpler program. And whatever program you have, you can keep modifying it until we reach that level, and we can simulate the whole thing. The idea is eventually to simulate the whole thing to see that, okay, you can develop the structures and it breaks up, and then it forms this from quantum level to relativistic level. All these things start forming. That's our eventual goal, but it will take a few years, I think, to get to that level. It requires higher level of programming and also simulations and modeling simulation and adjusting. But we don't want to put any arbitrary, what you call fuzzy factors, or any what you call as yeah. But we don't want to introduce any such things. Fudge factors, they call it.
Right.
No fudging. Fudging.
Yeah, I agree. Yeah. Yeah. So I don't think that the rectangle solution will work. I'm just sketching it out here. I don't think that's a possibility, because you're dealing with, on the one hand, two kind of abstract points that are. It's much more periodic and time-based, and the other one is like very much geometric and space-based.
Yeah, they may not be compatible, right?
I don't think they gel. Like, I can keep working on it, though. It might work. And the other thing, that's maybe some sort of rotation projection thing with a sine, cos, and tan could get us to where we want. So, because that would, it's a weird idea, though.
Yeah, I think there is a disconnect between algebra and the geometry itself.
Oh, yeah, it seems interesting, though. So, but one thing that I had in one of my papers was this concept that you can create these things called, what are they? They're like semantics. Anyway, they're waveforms, and it's a bit like what Stephen was going on with his harmonic series, where you have like 7 kind of octaves, well, 7 notes before
octaves.
Before you get to the octave. And
I think metrics protocol kind of touches upon these octaves. I come up with something called the nested loop, the nested, there's octave nested, octet nested, nest actually. Octet,
right.
The nest, that's what I use. So every time I do that, I become that. I can actually, it kind of moves around. It can be collapsed, and it can form the observable. This is in my mind. It works that way. and I'm trying to translate into mathematics and algorithm, you know.
Great. So it's like it's nested kind of fractal sevens in sevens.
And that's perfect, actually. That's why I get information. I don't know the alien or something, but somewhere I get this information. I put it in there. Bingo! I'm getting these algorithms, so to say, observable. You know, the tau thing, tau x, psi y. That's my observable. The tau is the energy thing. You know, like we talked the first one, and the psi is the wave function. So and the x. So I put that. I do permutation and feedback circuit.
Rajan,
it comes out.
Rajan, you dropped out there after you talked about when you brought up psi x.
Yeah, tau x, tau subscript x, tau subscript x.
What is the x?
X can be anything. Yeah, x is a table. I can put a table, but the x typically is the energy.
Okay.
Okay, but it can be other things also. And
right.
Then psi y typically is field, but it can be other things also. But there's a logic between the. If x is something, then y will be something. So there's a connection, logical connection between them.
Sure.
So you can do a logic statement like if x equal to energy, then y equal to field, like that. You know, if x is something else, then y is some. So it cannot be anything. You know, x and y are related.
Wouldn't you like relate energy with time?
No, in this case, field. So that when it's time, it's something else. I come up with a tesseract or tessellation or something. It's interesting.
Don't you have like
event? It's actually event.
What is?
X is event, then y is time. So that fits in with the quantum thing, quantum mechanics.